Uh, Hi, everyone. I'm an assistant professor in Department of Math and Statistics, as well as faculty in computing and data sciences. Typically in scientific applications, we think about more data being a good thing. And it usually is, right? We just got a bunch of examples from Kevin about how the more data we have, we can get new insights and maybe and new discoveries. For example, seems to be moving on its own. For example, in my own work, single cell data or whole genome data are examples, as well as all the ecological data that can be collected from satellites and other sources. However, sometimes more data can actually lead to more problems. It can lead to spurious findings, incorrect conclusions that the data seems to provide overwhelming support for, but actually is just leading to dead ends and kind of phantom discoveries. So why and how does this happen? Well, it really starts with statistical models that we use, okay? Statistical models give us a way of representing how data might have been generated. For example, on your left here, I have an example where we're trying to learn the history of a bunch of species, how they are related to each other, right? And so there's all these possible trees, and then we have to figure out how long ago they diverged. And so we need to fit all these different parts of the model together. All right, for some reason, this one isn't quite showing up correctly. There's supposed to be a bunch of big clusters of points in different colors that's representing different cell types that have been discovered. So the beauty of models is that they encode a lot of really useful information, and they can be interpretable. We can use scientific knowledge that we have to build them and get these insights. The challenge is that these models are always approximations to reality, right? They're never perfect. And so with a little data, things might look more like this pointless painting on the left here, where it's a little blurry, you squint, but it looks all kind of reasonable. However, once you start zooming in, once you have more and more data, you start to see the things that are not quite right, okay? And that's where problems can start. So I'll just give two quick examples of this. So the first is this phylogenetic tree problem, learning this tree, say based on the genomes of currently extant species. Well, it turns out that often a bunch of these trees might be pretty good explanations for the data you observe. But what will happen is that standard methods will just select one of these possible trees and be very confident that it's the best one. And if you get a slightly different set of data, it will select a completely different tree. And so you get these kind of contradictions. So here's an example where we showed that this bag posterior method could solve this problem. We split this data for whales into two halves. And it turns out these standard methods, they give completely different answers, but there's lots of overlap if you use the bag posterior. Here's a second example. Unfortunately, again, my dots are not showing up here, but here's this problem where we're trying to learn different cell types from measurements, in this case, flow cytometry data. And unfortunately, what happens is these models aren't perfect for clustering these different cell types. And so as you get more data, you start discovering, I should put in scare quotes, these spurious clusters of data that don't actually represent different meaningful cell types. So we developed a solution that solves this problem. The middle line there gives our kind of accuracy compared to the standard methods up above, and an alternative below. Our method has provable guarantees, plus it runs about 100 times faster. I think that's my last slide. So anyway, this is an area that my group is working a lot in because unfortunately, again, these methods, they seem like they're working really well. There's often no obvious sign that something's gone wrong. So we need these alternative methods that still let us gain as much information as we can from the data, while also not running into incorrect conclusions.